Good morning, students. I, Dr. Rani Jindal, working as Assistant Professor in Government PG College for Women Sector 14, Panchkula. Today we continue third lecture of Ionic Solid, BSc first semester in Organic Chemistry, fourth chapter. The topic of today's discussion is radius ratio effect and lattice defects. So, first is the radius ratio effect and coordination number. Radius ratio is an important parameter to predict the coordination number from the relative sizes of ions in ionic structure. Ionic solids are made up of cations and anions which have definite arrangements. Each ion is surrounded by a number of ions of opposite charge. Next is the radius ratio effect. The ratio of the radii of the positive and negative ions is called the limiting radius ratio. Limiting radius ratio is equal to radius of cation upon radius of anion. The effect of radius ratio in determining the coordination number and shape of the ionic crystal is known as radius ratio effect. On the basis of limiting radius ratio, the coordination number and shape of the ionic crystals can be obtained. If the value of the limiting radius ratio lies between 0 to 0.155, then coordination number is 2, shape is linear. And if the limiting radius ratio lies between 0.155 to 0.225, then the coordination number is 3 and the shape is trigonal planar. Example is B2O3. If the limiting radius ratio is 0.225 and 0.414, then the coordination number is 4 and the shape is tetrahedral. Example is zinc oxide, copper chloride, etc. If the limiting radius ratio lies between 0.414 to 0.732, then the coordination number is 6, then shape is octahedral and examples are sodium chloride and magnesium oxide. If the limiting radius ratio lies between 0.73 to 1, then the coordination number is 8 and the shape is body centered cubic. Examples are cesium chloride, ammonium bromide, etc. Next is for example, the radius of sodium ion is 0.95 angstroms and that of chloride is 187 angstroms. Then the radius ratio in sodium chloride is 0.52. If the radius ratio is 0.524, therefore the coordination number is 6 and the shape is octahedral. And it is also proved by X-ray study that the sodium chloride crystal and each sodium ion is surrounded by 6 chloride ion which are arranged octahedrally, and each chloride ion is surrounded by 6 sodium ions. Next is what is the significance of radius ratio? With the help of radius ratio, we can determine the coordination number, structural arrangement and the geometry of a ionic solid. Next is the effect of variation of size of anions and stability of the structure. The most stable arrangement is one in which the anions are touching each other and the cations simultaneously. In this case, the attraction will be maximum and repulsion will be minimum. If the size of the cations is less, the anions will no longer touch cations simultaneously and the structure will be unstable. Similarly, if the size of the cations is large, the anions will be no longer touch other anions. The structure will be unstable as shown in the diagram. Next is the effect of decrease in radius ratio on the coordination number of the compound. Change in the radius ratio changes the structure of the compound. The most stable arrangement is one in which the anions are touching each other and the cations simultaneously. Now, if decrease the radius ratio either by decreasing the size of the cation or by increasing the size of the anion, then the structure will become unstable. All the anions will not able to touch simultaneously the cation. In order to touch the cation, the anion have to go closer and closer, and therefore repulsion will increase. When the radius ratio is further decreased, a stage will reach when one or more anion may be pushed away so that remaining anions fit around the cation, giving more stable structure. In other words, there may be a change in coordination number from 6 to 4. This is effect of decrease in radius ratio on the coordination number. If we decrease the coordination number, if we decrease the radius ratio, the coordination number also decreases from 6 to 4. Next is the effect of increase in radius ratio on the coordination number of the compound. If we increase the radius ratio either by increasing the size of the cation or by decreasing the size of the anion, the structure will become unstable. All the anions will no longer be touching one another. If the radius ratio is further increased, the anions will be going farther and farther apart. Consequently, a stage may reach when more number of anions may be able to fit around the cation, giving more stable structure. In other words, there may be change in coordination number from 6 to 8. It means if we increase the radius ratio, the coordination number of the compound increases. This is in figure a factor of increase in radius ratio on the coordination number. If we increase the radius ratio, the coordination number of the compound increases. Then what is the limitations of radius ratio rule? Although radius ratio rule is useful concept for predicting and understanding the structures of ionic compound, yet it is not perfect. It has many limitations. Number 1, the radius ratio rule applies only to the packing of hard spheres of known size. This is far from reality. Anions are not hard but are polarizable. Under the influence of cations, the extent of polarization of the anion leads to covalency and result in serious error in the application of radius rule. For example, the radius ratio of silver iodide is 0.52. This indicates the coordination number of 6, means sodium chloride structure, but actually silver iodide is 4 coordinated tetrahedral lattice with zinc blend structure. Similarly, cadmium sulfide, mercury sulfide and zinc oxide have radius ratio values greater than 0.5 but have tetrahedral structure. Second, many serious errors occur for the coordination number 6 versus 8. Coordination number 8 is found only in cesium chloride, cesium bromide and cesium iodide. Although radius ratio calculation predict cesium chloride coordination number 8. Structure for oxides of large divalent metal ions such as barium 2 positive, strontium 2 positive and lead 2 positive. Yet no 8 coordinate oxide molecular orbital had observed. Limitation of third limitation is radius ratio rule failed to explain why some compound crystallize in more than one modifications having different coordination number. For example, thallium chloride crystallize in two forms adopting sodium chloride structure having coordination number 6 with internuclear distance 3.15 angstroms and cesium chloride structure having coordination number 8 internuclear distance 3.32 angstroms. Fourth, effective radius of a cation is greatly influenced by the anions so that radius ratio changes. For example, silver fluoride and sodium fluoride crystallize out in sodium chloride type structure with coordination number 6. Now, if we assume that the size of fluoride ions remain constant, then silver positive is bigger than sodium positive. On the other hand, for a given size of chloride ion in silver chloride and sodium chloride, size of cations are reversed. For example, sodium positive ion is bigger than silver positive ion. Then next topic is lattice defects. Ionic crystals have well-defined order of the constituent ions. An ionic crystal which has the same unit cell containing the same lattice point throughout the whole of the crystal is known as ideal crystal. However, such ideal crystals exist only at absolute zero, means 0 degree Kelvin temperature. At any temperature above 0 degree Kelvin, the crystals have some departure from the ordered arrangement. Any deviation from completely ordered arrangement in a crystal constitutes a disorder or a defect. The crystal may have additional defect due to the presence of some impurities. These imperfections will not only change the properties of the crystals but also give rise to new properties. There are commonly two types of defects in crystals. First one is defect in stichometric crystals. Second defect is defects in nonstoichiometric crystals. First is defect in stichometric crystals. Stichometric crystal compounds are those in which the number of positive and negative ions are exactly in the ratio indicated by the chemical formula. The defect in this type of compounds are called stichometric defect. Two types of defects are generally observed. Number one, Schottky defect. Second is Frankel defect. First is Schottky defect. This defect was observed by German scientist Schottky in 1930. It arises if some of the atoms or ions are missing from their lattice sites. The lattice sites which are unoccupied are called lattice vacancies or holes. Since the crystal is to remain electrically neutral, equal number of cations and anions are missing. The ideal AB crystal and the existence of two holes, one due to missing cation, other due to missing anion, is called Schottky defect. The Schottky defect is strongly observed in ionic compound having high coordination number and ions having similar size. For example, sodium chloride, potassium chloride, potassium bromide, and cesium chloride ionic solids have Schottky defects. It has been observed that in sodium chloride there are about 10 raised to power 6 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube there are about 10 raised to power 22 ions, and this means that there will be one Schottky defect per 10 raised to power 16 ions in sodium chloride. Because of this, large number of vacancies in crystal and its density is markedly low. This is a ideal crystal. First one in figure. First one is in ideal crystal and the second is a Schottky defect in crystal. And there is a cation vacancy and anion vacancy. Electrical neutrality is maintained. Second is the Frankel defect. This defect was observed by Russian scientist Frankel in 1926. It arises when an ion is missing from its normal position and occupies an interstitial site between the lattice point. The existence of one hole due to missing cation from its normal position and occupying an interstitial position, as in the figure, the crystal remain electrically neutral because number of cations and anions remains the same. There is a cation vacancy and cation in interstitial site as shown in a figure. This is a Frankel defect. Next is the conditions causing Frankel defect. This defect generally occurs in compound in which the coordination number is low. Second, anions are much larger in size than the cations. In pure alkali metal halides, these defects are not very common because the ions cannot get into the interstitial position due to their large sizes. These defects can be found in silver halides such as silver chloride, silver bromide, silver iodide, etc. Because of small size of the silver positive ion, it can go into the interstitial sites. Next is the vacancies or holes are present in a crystal with Schottky as well as Frankel defect, but the former leads to decrease in the overall density of the substance, but the later does not. In certain ionic solid such as silver bromide, both Schottky and Frankel defect occur. Next is the defect in nonstoichiometric crystals. The compound in which the ratio of positive and negative ion present in the compound different from that required by ideal chemical formula of the compound are called non-stoichiometric compounds. The defects in these compounds are called non-stoichiometric defects. For example, vanadium oxide has the formula VOX where X lies between 0.6 and 1.3. Similarly, iron 2 oxide sample contain more oxygen atom than the iron atoms, while sample of zinc oxide usually has the excess of zinc atoms than oxygen atoms. There are two types, whether positive ions are in excess or negative ions in excess. These are known as metal excess defects or metal deficient defects respectively. So we discuss one by one. First is the metal excess defects. In this defect, the positive ions are in excess. Anion vacancies. In this case, negative ion may be missing from their lattice site, leaving holes in which the electron remain entrapped to maintain the electrical neutrality. Evidently, there is an excess of positive means metal ions. Although crystal as a whole is electrically neutral, this type of defect is observed in those crystals which are likely to form Schottky defect. For example, alkali metal halides anion vacancies are produced when alkali metal halide crystals are heated in the atmosphere of alkali metal vapors. The metal atom gets deposited on the surface of alkali metal halide crystal. The halide ion move into the surface and combine with the metal ions. The electron thus produced by the ionization of the metal atom diffuse into the crystals and get entrapped at the anion vacancies. The electron trapped in anion vacancies are known as F centers. This is the figure. Electrons remain trapped in anion vacancy as shown in the diagram. This is metal excess defect due to anion vacancy. Next is the extra cations occupying interstitial sites. In this case, there are extra positive ions occupying interstitial sites and the electrons in another interstitial sites to maintain the electrical neutrality. This type of defect is found in crystals which are likely to develop Frankel defect. The common example is zinc oxide. Zinc oxide loses oxygen reversibly at high temperature and turns yellow in color. The excess zinc 2 positive ions are trapped in interstitial sites and equal number of electrons are trapped in the neighborhood to balance the electrical charge. These electrons give rise to enhanced electrical conductivity. So this is the metal excess defect due to extra cations and electrons in interstitial sites. Next is consequences of metal excess defects. Number 1. The crystals with metal excess defects conduct electricity due to the presence of free electrons. However, the conductivity is very low because of the number of defects, and therefore the number of free electrons is very small. Because of low conductivity as compared to the conductivity of metals, these are called semiconductors, and these compounds are called n-type semiconductors since the current is carried by the electrons in the normal way. Second is the crystals with metal excess defects are generally colored. For example, nonstoichiometric sodium chloride is yellow and nonstoichiometric potassium chloride is violet. Next is the metal deficient defects. These contains less number of positive ions and the negative ions. These arises due to two ways. Number 1, cations vacancy. In some cases, The positive ion may be missing from their lattice site. The extra negative charge may be balanced by some nearby metals ion acquiring two positive charges instead of one. The common examples of the compound having these defects are ferrous oxide, ferrous sulfate, nickel oxide, etc. In, in case of iron pyrides, for example, 2 out of 3 ferrous ions in a lattice may be converted into Fe3 positive state and the third Fe2 positive ion may be missing from their lattice site. Therefore, the crystals containing Fe2 positive and Fe3 positive ions, this give rise to exchange of electron from one Fe2 positive ion to Fe3 positive changes to Fe2 positive changes to Fe3 positive and Fe3 positive changes to Fe2 positive ion. As a result, crystal has a metallic luster. Excess anion occupying interstitial sites. In this case, extra anion may be occupying interstitial positions. The extra negative charge is balanced by extra charges. Oxidation of equal number of cations to higher oxidation states on the adjacent metal ions. This is the metal deficient defects, cation vacancy and metal occupying the higher, acquiring the higher charge. Metal deficient defect due to extra anion. Anion occupying the interstitial site and the metal acquiring the higher charge. This is the consequences of metal deficient defects. Crystals with metal deficient defects are called semiconductors. The conductivity is due to the movement of electrons from one ion to another. When an electron moves from A positive, it changes to A2 positive. It is also called movement of positive hole and the substances are called P-type semiconductors. The conductivity of semiconductors is mainly due to the presence of impurities and defect. The semiconductors are very important solid state material having many important applications in electronics. Then this is the questions for your assignment. First question is write a note on radius ratio rule. Second question is how are metal deficiency defects created in ionic crystals? Third question is what are Frankel defects? Thanks.